One type of haloalkane which was very much in the news a few years ago, not so much now because the world has other problems, but was chlorofluorocarbons. That means compounds like this, for example. So a compound in which you have no hydrogens bonded to the carbons, they were just fluorines and chlorines. And these compounds used to be used extremely widely because they had lots of beneficial properties. So for example, it's virtually non-inflammable, it's non-toxic, and you know, it had all sorts of useful applications as a refrigerant, as a gas for blowing bubbles in polystyrene, for example, as a propellant in aerosols. Again, was very widely used for that. And then, unfortunately, people discovered that these things were doing something very bad to the planet, which was very far from obvious because it was happening in the upper atmosphere. And what they were doing was catalyzing the destruction of ozone. And ozone is oxygen, but O3 rather than O2 in the upper atmosphere. And that was a problem because ozone has a very important role in the upper atmosphere, in that it absorbs ultraviolet light very effectively. So most of the ultraviolet light that comes in from the sun is absorbed by ozone high up in the atmosphere there, and that means it doesn't reach the Earth's surface. If it did, life as we know it would essentially not be possible because that ultraviolet light has a very bad effect on DNA. It causes mutations, and so you wouldn't be able to have a stable genetic code, and there would be big problems for, as I say, life would have had to evolve in a completely different way. So if ozone concentrations decrease in the upper atmosphere, that's a problem for us because we then become susceptible to mutations, and that, for example, could cause cancers, particularly skin cancers. So people were very worried about this, and once the chemistry was established and there was an overwhelming case in place that these were the culprits, they were banned by international treaty. And you therefore need to know about the chemistry and know why it was important. So the destruction of ozone depends actually on not the chlorofluorocarbon directly, but on the product of what happens to that when the ultraviolet gets to it. So remember, these things are all happening in the upper atmosphere, and the idea is that these compounds were used on the Earth's surface, but once they were released, for example, once you sprayed your aerosol, they would gradually diffuse upwards, and when they got up to the upper atmosphere, there was a lot of UV up there. And you know from stuff that you've done earlier on when we did radical substitution, that UV can break bonds open homolytically to make radicals, and that's what it did here. Carbon-chlorine bond is weaker than the carbon-fluorine bond, so that's the one that tends to break, and so you get this process. And that generates radicals. And as you know, radicals are extremely reactive, and they will tend to react with whatever they bump into. Now this can do various things, but we're not going to focus on that, because the only one you need to know about, because it actually is the one that does most of the damage, is the chlorine radical. So let's have a look at, you need to know this is how they're created, and then you need to see how they attack the ozone. So this is the first reaction. Cl dot reacts with O3 to produce ClO dot plus O2. So that's very similar to one of the reactions that you learnt in radical substitution, where again you had a chlorine radical and it bumps into a molecule and takes one atom out of it. So in this case it takes one oxygen atom out of the O3 to give you ClO dot and leaves you with O2. And just as in radical substitution, you have ClO dot is still a reactive species, so it can then go on and react with something else. Now there are all kinds of things that actually go on, but in this very simplified version, one of the most common things that can happen is that it can encounter an oxygen atom. Now you might think that's a bit weird because you don't usually meet oxygen atoms. Oxygen's normally in the form of molecules, but remember this is in the upper atmosphere. So everything's constantly being bombarded with UV light, and that means oxygen molecules are being broken open to make oxygen atoms. So there are actually quite a lot of these up there. So it's not unreasonable that one of these should meet one of those. So the ClO has been formed by this reaction. The oxygen atom is just there as a result of UV breaking oxygen molecules open. And the effect of that is that you get Cl back plus another molecule of O2. And you can see that those two reactions can follow each other as a chain reaction, because Cl dot then goes back into there. Okay, so this is like a propagation sequence. Okay, so it's a propagation step in the reaction. And if we add those two together, so we add together everything on the left hand side, we get O3 plus O plus Cl dot plus ClO dot. And then we add together everything on the right hand side, we get 2O2 plus Cl dot plus ClO dot. And you can see that we can cancel because Cl dot is on both sides, and so is ClO dot, and so what we get is the overall reaction, which is that. So the ozone is destroyed and converted by reaction with atomic oxygen into two molecules of O2. So what the Cl dot has done in this reaction is act as a catalyst, because you can see that it made the whole thing possible. This reaction would not have taken place, at least not in this kind of way, without the Cl dot being there, because it had to react with the ozone first in order to create this, which then led to the whole thing happening. But the crucial thing is the Cl dot was then regenerated. So overall, the concentration of Cl dot doesn't change, it's not used up, and therefore it's a catalyst. And that's really important, because what it means is that these chlorofluorocarbons are very effective at destroying the ozone, because they're not used up. So a single molecule of this can destroy loads and loads of molecules of ozone. Hundreds of thousands of them before some other reaction might destroy it in an irreversible way. And that's why they've relatively small amounts of these in the upper atmosphere were able to wreak such havoc. So you need to know this story, you need to know why it's important, but crucially you need to learn this mechanism. So CFCs, chlorofluorocarbons, were banned something like 20 years ago, and very slowly the atmosphere is starting to recover, but it really is only in the last few years that that's been significant. Nevertheless, the ozone concentration is becoming more stable at a reasonable level. However, the problem of man-made damage to the ozone layer hasn't gone away, because unfortunately there are other gases which we are still producing which cause something very similar to happen. And the other one that you need to know about is nitrogen monoxide. So this is formed essentially by this reaction. And that happens when there's extreme heat. Basically, it allows the oxygen and the nitrogen in the air to react with each other to produce NO. And so it happens in engines. It happens on the ground in petrol engines to some extent, and then this normally gets oxidized to NO2 and ends up causing other kinds of problems like acid rain and stuff like that. But in a jet engine up in the atmosphere, in an aeroplane high up in the atmosphere, the NO is in a position to interact with ozone. And basically it's able to do that because it's a radical. If we do the dot and cross diagram for NO, you can see how that works, because oxygen as usual will form two bonds, right, because it's got 6 electrons in the outer shell, so it's going to tend to want to share 2 pairs to take it up to 8, so we get a double bond here. The oxygen then has 2 lone pairs, and that's it fully accounted for. Now if we look at what's happened to the nitrogen, it's in group 5, so it had 5 outer shell electrons, it's used 2 of them here, so it will have that. So it has an unpaired electron. So NO is an example of a compound which is also a radical, and because it's a radical it can do what Cl dot does. So we can actually learn how this causes destruction basically by just saying, right, whatever Cl dot does, NO does it too. And it's much better to learn it that way rather than learn it as a separate thing, because it's just much simpler. So you just think, right, NO is going to do this instead, and again it will just take 1 oxygen out of the O3 just like Cl dot did, and you can see what that will produce is NO2, which is also a radical, plus O2, and then the NO2 will do what the ClO did and produce O2 and regenerate the NO. So we get the same kind of chain reaction in which the NO2 from here feeds the second reaction, that regenerates NO, which then feeds the top reaction. So again, if we just add the two together, you can see it's going to work exactly the same way. O3 plus O plus NO plus NO2. Adding together all the things on the left hand side gives you 2O2 plus NO plus NO2. And again, you can see that the radicals cancel out, because NO is used up here but regenerated there, NO2 is generated here but then destroyed there, and what you end up with is that same destructive reaction overall. So you need to know that as well, that that's an ongoing process caused largely, I mean it happens naturally to some extent. Lightning, for example, can also cause this reaction to happen, so it is a natural process, but it's happening to a greater extent because of NO produced by aeroplanes, jet engines.